In this video, we are going to discuss the different types of chemical reactions. And there are 5 main types of chemical reactions, and we are going to first talk about the general form that they take. So the first type of reaction is called a synthesis reaction. Synthesis. And in this reaction, there are 2 elements or compounds that are coming together to form a larger compound. So in synthesis, our general form for that reaction takes something A plus B reacts together to form AB. So that's the general form, 2 smaller things coming together to form a larger compound. Then we have the opposite of synthesis, sort of, which is decomposition. And decomposition is just the flip of synthesis. So we have AB, we have our larger compound, breaking down into 2 smaller things. Or, sorry, A plus B here. Sorry for that mistake there. So we have AB yields A plus B. This larger thing is breaking down into 2 smaller things. And most of the decomposition reactions we will look at is a compound breaking apart into its elemental components. The third type of reaction is a combustion reaction. And combustion is burning, so when we are burning something. And a combustion reaction always has the same 2 products and always has one of the same reactants. So when we get to predicting products, it will be very simple to predict the products of combustion reactions. But actually, combustion reactions are usually the most difficult ones to balance. So that's the tricky part. But a combustion reaction, we always start with something called a hydrocarbon. And that is a compound that contains the elements of hydrogen and carbon, and it also can contain other elements like nitrogen and oxygen and phosphorus sometimes, but they always contain hydrogen and carbon. So we have a hydrocarbon as one reactant, and then plus oxygen. And oxygen is a diatomic molecule, so when I say oxygen, I mean O2. So we have a hydrocarbon plus O2, and a combustion reaction always gives us the same 2 products. So instead of using A and B here, I'm going to put the products. They are carbon dioxide and water. CO2 and H2O. So a combustion reaction, the reactants are a hydrocarbon and oxygen, yielding products of carbon dioxide and water. So then our 4th type of reaction is a single replacement reaction. Single replacement. And in a single replacement reaction, we have a lone element and we have a compound. So I'm going to represent the compound as AB, and I'm going to represent our lone element as C. So we have AB plus C. And then what happens in a single replacement reaction is that the lone element replaces something in the compound that is less reactive than itself. So our lone element is going to replace the less reactive element in our compound AB. So our products from this reaction are going to be AC. So C has come in or replaced B, and then kicking B out by itself. So we have AB plus C. C comes in, replaces B, so then our products become AC plus B, with B kicked out by itself. We then have a second type of replacement reaction called double replacement. Double replacement. And in double replacement, we actually have 2 ionic compounds, and you can think of them as switching partners. So we start with AB and CD, and the cations of these 2 ionic compounds swap places. So A comes over and pairs with D, and C comes over and pairs with B. So we are going to get AD plus CB as our products from that reaction. And we'll go into more detail about these types of reactions in just a second, but I just want to make sure you have a summary of all 5 reaction types in one place. So let's start by talking about replacement reactions. So a single replacement reaction occurs when a lone element replaces a less reactive element in a compound. And when we are looking at single replacement reactions, it's important to remember that cations, or positively charged ions, can only replace other cations in a compound, and anions, or negatively charged ions, can only replace other anions. So for a reaction to occur, the lone element, the thing by itself, must be more reactive than the element being replaced. And to determine whether or not something is more reactive, we look at something called the activity series, which you will get on your test. So this is the activity series that you will have, and it just shows the order of elements by reactivity. So something that's closer to the top is more reactive than things below it. So for instance, lithium is the most reactive element on the activity series in the cations portion. And you might notice that hydrogen is also in the activity series. It is the only non-metal cation in your activity series, and it fits right in here between lead and copper. And then down here you have your anion activity series listed from most reactive to least reactive. And notice that these also are in the same order on your periodic table, with fluorine all the way up at the top of the periodic table, and then as you go down, things becoming less reactive. So basically, for a element to replace something in a substance, it has to be higher in the activity series than the thing that it is replacing. So let's look at a couple of examples. So in example 1, we have potassium chloride reacting with lithium. And so to determine, we can go ahead and predict the products of this reaction before we determine whether or not it will occur. We can predict what the products would be regardless, but then at the end we do have to determine whether or not this reaction would actually occur if we put lithium in with potassium chloride and try to react them together. So potassium chloride and lithium, lithium is a cation, so it can only replace a cation. So out of potassium chloride, potassium is the cation. So lithium is going to try and replace potassium. So I'm going to draw an arrow here, and then potassium is going to be kicked out by itself. So if this reaction occurred as planned, we'd have lithium and chlorine bonded together. So we need to re-crisscross because lithium may not have the same charge as potassium. So lithium and chlorine, if I look at my periodic table, I can determine the charge of both of these things. Lithium is in group 1 of the periodic table, so it has a +1 charge, and chlorine is in group 17, giving it a -1 charge. So when I crisscross, I get LiCl. And then poor potassium has gotten kicked out by himself, so he is just going to be an element potassium. So now I need to determine whether this reaction will occur or not. And for this reaction to occur, remember lithium has to be more reactive than potassium, meaning that lithium has to be higher than potassium in my activity series. So on my way up my activity series, there's potassium, and then lithium's all the way up at the top. So lithium is indeed more reactive than potassium, so this reaction will occur. So I'm going to put Rx in. This reaction will occur. Now let's look at example number 2. Once again, we have potassium chloride, but now potassium chloride is trying to react with sodium. So if this reaction were to occur, sodium would replace the cation, potassium, and potassium would be kicked out by itself. So we need to redo our crisscross to predict our products. Sodium is going to bond with chlorine. So Na has a +1 charge, and chlorine has a -1 charge. So when we do our crisscross, we get NaCl. And then potassium is going to be kicked out by itself. So now we just need to determine whether or not this reaction will occur. And so I need for sodium to be higher in the activity series than potassium. So I'm looking at my activity series, and sodium is down here, and then potassium is up here. So sodium is lower in the activity series, meaning it is less reactive than potassium. So although we predicted these products, this reaction will not occur. So I'm going to put no reaction here. So you can predict products for all sorts of single replacement reactions, but in order to determine whether or not they will actually occur in practice, you need to check the activity series to make sure that the element that is by itself is actually more reactive than the element that is in the compound already. Next, we're going to talk about double replacement reactions. And a double replacement reaction occurs when the cations of two ionic compounds swap and pair with the opposite anion. So for a double replacement reaction to occur, there are several things that have to kind of be occurring. So first of all, for the reaction to occur, both of the reactants must be soluble, meaning that they are able to dissolve. And when we're talking about able to dissolve, usually we are talking about able to dissolve in water. Water is the universal solvent, and very close to all of the reactions that we look at least in this class, will be occurring in water as a solvent. So that's the first requirement, is that for the reaction to occur, both reactants must be soluble. And there's a second requirement that one of the products of the reaction, not both of them, but just one of them, must either be insoluble in water or must be water. So the reason for this is that there are two main types of double replacement reactions. And the first type of double replacement reaction is called a precipitation reaction. And this reaction produces an insoluble salt that's known as a precipitate. And so when we look at a precipitation reaction in the lab, what you'll notice is that when you pour the two reactants together, you all of a sudden see this cloudy substance. And that's not the two things just with air in them. That's actually a new substance forming as part of the reaction. That cloudiness is due to the precipitate, which is a solid, because it is insoluble in the reaction mixture. So it falls out of solution. That's what we say. It falls out of solution as a precipitate. So that is one type of reaction. And then the second type of reaction is a neutralization reaction. And in neutralization, we're reacting an acid and a base together to be neutralized. And when a neutralization reaction happens, it produces a soluble salt, so you won't see it because it's still dissolved in the mixture, and it also produces water. So we go from an acid and a base reacting together to produce essentially salt water. Not salt as in sodium chloride like in the kitchen, but it can be all sorts of different salts. But those are the two main types of double replacement reactions. So just to recap, for a double replacement reaction to occur, both of the reactants have to be soluble, and one of the products either has to be insoluble or has to be water. Otherwise, the reaction won't occur. So let's look at a couple of examples here, and let's also look at something called the solubility rules. So you probably are thinking right now, hey, I have no idea whether or not something is going to be soluble. I don't know whether or not it's going to dissolve. And you have a series of rules that you can use to determine whether or not something will be soluble. And this set of rules is kind of confusing, to be honest, and there's no really good way of organizing them. You can look up different organizations online, but this is the one that I'll have for you to use in class. But we'll just use this series of rules to guide our process as we go through these examples. So in example 1, we have lithium bromide reacting with rubidium oxide. And so we first need to decide what the products would be if the reaction were to occur. And to do this, we will pair the cations with the opposite anion. So what I like to do is draw arrows. So I know that when these two things swap, that rubidium is going to be pairing with bromine, and lithium is going to be pairing with oxygen. So if this reaction were to occur, lithium and oxygen are going to be bonded together, and rubidium and bromine are going to be bonded together. So I have to recross to figure out my products. I have to redo my crisscross because rubidium and lithium may not have the same charge, and oxygen and bromine may not have the same charge, so we have to recross and double check our charges with our periodic table. So I'm going to first do lithium with oxygen. So lithium has a +1 charge because it's in group 1, and oxygen has a -2 charge. So when I do my crisscross, I'm going to get Li with this 2 coming down, and then just 1 oxygen. So notice I now have a difference in my number of lithiums on either side of my equation, which I will need to correct by balancing my chemical equation. But we'll first finish writing the products, and then I'm going to put parentheses to put my state symbol in, because in double replacement reactions, it's really important to show the state symbols so that someone would know whether or not that reaction would occur. So I have lithium oxide, and my second product is going to be rubidium and bromine. So I have Rb and Br. Rubidium has a +1 charge, and bromine has a -1 charge. So when I do my crisscross, I get Rb, Br. And I'm going to put my parentheses for my state symbol. Now that I've predicted my products, I need to determine whether or not this reaction will actually happen. So looking back up at our notes, it says for the reaction to occur, the first requirement is that both the reactants must be soluble. So I need to determine if lithium bromide is soluble. So I look at my solubility rules, and the first one on my sheet says all compounds of lithium, sodium, potassium, rubidium, cesium, and ammonium are soluble. And there are no exceptions to that rule. So lithium bromide is a compound of lithium. So I'm going to put aqueous, meaning that it can dissolve in water. Then I need to check rubidium oxide. So that also goes with this first rule. Rubidium oxide is a compound of rubidium, and there are no exceptions. This is also aqueous. So this reaction meets the first requirement. Both reactants are soluble. So now I need to look at my products. So one product either has to be insoluble or be water. So just glancing at this, neither of my products are water. So I need to look for an insoluble product. So lithium oxide, once again, it follows this first rule that all compounds of lithium are soluble. So I know this one's going to be aqueous. There's no exceptions to that rule. And rubidium bromide. Rubidium, all compounds of rubidium are soluble. So this one's also aqueous. So we don't have an insoluble product. So this reaction will not occur. So I'm going to put no reaction, or no Rxn on this one. Although we predicted accurate products, in practice, this reaction will not actually occur. But then let's look down at example 2. Silver nitrate reacting with lithium bromide. So we first need to predict what our products would be. So if we connect our cations with their opposite anions, so lithium is now going to be bonded with nitrate, and silver is now going to be bonded with bromine. So if we redo our crisscross on the other side, we will get silver, Ag +1, and bromine, Br -1. So when we crisscross those, we just get Ag, Br. And I'll put my parentheses for my state symbol. And then next we have lithium pairing with nitrate. So Li with a +1 charge, and NO3 with a -1 charge. So we get LiNO3 and I'll put my parentheses for my state symbol. So now we have to make sure this reaction will actually happen. So both of our reactants must be soluble. So let's check that first. AgNO3. So looking at my list of solubility rules here, I don't see anything about silver or nitrate in this first rule, so I'm going to go down to the next one. And it says all compounds of NO3 and C2H3O2 are soluble. They generally dissolve in water. So there are no exceptions to that rule, so I know that silver nitrate must indeed be soluble or aqueous. Then in checking lithium bromide, it still follows that first rule that all compounds of lithium are soluble. So that's also aqueous. So we meet that first requirement. Both reactants are soluble. So next we need to look at the products. And one must either be insoluble or be water. We don't have water here, so we need to meet that insoluble product requirement. So we have silver bromide, AgBr. So looking down our list of rules, I don't see anything in these first two, but the third one says compounds of chlorine, bromine, and iodine generally dissolve in water. But then there's exceptions to the rule, and an exception to the rule is silver. So silver bromide, although most compounds of bromine dissolve, silver bromide does not dissolve in water. So it is insoluble. So instead of putting aqueous, I'm going to put S to indicate that it's going to be a solid product. So this reaction will occur because we have one insoluble product. So let's just check lithium nitrate and make sure that it is aqueous, and that's a compound of lithium, so all of them are soluble. So this will be aqueous. So this reaction will occur. So I'm going to put Rx in to indicate that we will have a reaction. So predicting products of replacement reactions can be a little bit tricky, but it becomes much easier the more you practice. So when you go through your practice sheet today, try and do it without watching the video. Try and do it using your solubility rules and using your activity series, which is right here. And try and do them yourself to make sure that you can feel comfortable doing this on your quiz. Next, let's look at synthesis and decomposition reactions. So a synthesis reaction is when there's a direct union of two elements, and it will yield a binary compound. Usually it will be a binary ionic compound, but to know that, you just look to see that there is a metal. And you can tell that you have a synthesis reaction when there are two lone elements. So here we have sodium and we have chlorine. And here we have calcium and sulfur. So both of these examples, there are just two lone elements. So this must be a synthesis reaction. So all we're going to do is we're going to put these two things together in a compound. And when we do that, we have to redo our crisscross. So sodium and chlorine are going to come together. So sodium has a +1 charge and chlorine has a -1 charge. So when we crisscross, we get NaCl. The biggest mistake that students make on synthesis and decomposition reactions is that you forget to redo your crisscross, and so students write NaCl2. But that's not correct because that is not correct balance of charge. So we have to redo our crisscross, Na plus with Cl minus, and we get NaCl. And then if we wanted to balance our reaction, we see that there are two chlorines over here, so we need to put a 2 out in front over here, and then that makes 2 sodium, so we'd have to fix that with a coefficient in front of sodium. So redo your crisscross, and then at the end, go back and balance your reaction once you already have predicted your products. Looking at the second example, we have calcium and sulfur. So calcium has a +2 charge, and sulfur has a -2 charge. So when we crisscross, we're going to get Ca2S2, but that reduces to just CaS. So here, the equation is actually already balanced. We have 1 calcium on each side and 1 sulfur on each side. Then let's look at decomposition. So you'll know it's a decomposition reaction when there's only one reactant. And binary compounds break down into their component elements. And that's the most common type of decomposition reaction that you will see. But you also may see a few reactions that have carbonates breaking down, like calcium carbonate. And carbonates always break down into carbon dioxide and then an oxide of the compound that you started with. So it would break down into carbon dioxide and calcium oxide in this case. But there are lots more types of synthesis and decomposition reactions, but in order to predict the products of them, you really just have to memorize what the products are. So these are the only types that I expect you to know this year. So let's look at these examples. So this first one, magnesium oxide, that is just a binary ionic compound. So it is just going to break down into its component elements. So it's going to break down into magnesium and oxygen. But oxygen can't ever really be by itself. It is diatomic. So we're going to put O2, diatomic oxygen, molecular oxygen. So then our equation's unbalanced. So we need to come back over here and put a 2 in front of MgO, and then a 2 in front of magnesium to balance our equation. And then finally down here we have calcium carbonate, and all carbonates break down into CO2 and an oxide. So I'm going to put CO2 first, because that's the easy one to predict, and then we need to figure out what calcium oxide would look like. So we need to crisscross. We have calcium with a +2 charge, and we have oxygen with a -2 charge. So in this case, we would get CaO, CO2 plus CaO. And this equation is actually already balanced. We have 1 carbon on each side, we have 1 calcium on each side, and we have 2 oxygens here and 1 oxygen there, for a total of 3 oxygens. So last but not least, let's talk about combustion reactions. So remember, combustion reactions, you will always have a hydrocarbon, meaning a compound that's made up of hydrogen and carbon, and sometimes some other things like oxygen and fluorine. I'm blanking on other elements, but phosphorus, things like that. But always hydrogen and carbon plus oxygen. And the combustion reactions always have the same 2 products, which are CO2 and H2O. So once you identify that it is a combustion reaction, putting the products is very, very simple. We just have to know that it is a combustion reaction. So here in example 1, we have CH4 plus O2. So we have a hydrocarbon, meaning that it contains hydrogen and carbon. And we have oxygen, so we know it's a combustion reaction. And the products will be CO2 and H2O. The trickiest thing about these is balancing. So let's go ahead and make sure this is balanced. So we have 3 oxygens over here, so that's out of balance, and 4 hydrogens, 2 hydrogens. So I'm going to go start by fixing the hydrogen by putting a 2 in front of that. And then we have 1 carbon on each side. So then I just need to fix oxygen. We have 2 oxygens in CO2 and 2 now in H2O, so that's 4 total. So I'm going to double this over here to balance my equation, giving me the same number of carbons, hydrogens, and oxygens on both sides. Let's look at the second example. Here we have another hydrocarbon, meaning hydrogen and carbon plus oxygen. So we know this is going to yield CO2 and H2O. But let's look at balancing this. So the first thing I notice is that carbon is out of balance. So I'm going to fix that by putting a 3 over here. And then I notice that hydrogen's also out of balance. So we want to fix that. And I'm going to put a 3 right here. 2 times 3 is 6, so 6 and 6. And then last I have oxygen out of balance. So now my total oxygens over here is 6 in CO2. And then 3 in H2O. So 6 plus 3 gives me 9. And that's kind of a problem because I have O2 over here, and there's nothing I can multiply by 2, not a whole number anyway, that'll give me 9. So, what I'm going to do is I'm going to put a fraction or a decimal number here for a second. So half of 9 would be 4.5. So I'm going to put that there, but I know that I can't have a decimal value to balance my equation. It has to be all whole numbers. So what I'm going to do is I'm going to take all of my coefficients and multiply them by 2, so that then this will be a whole number, and everything else will be in proportion 2O2. We'll have a correct mole ratio. So I have to remember that I do have a coefficient in front of my hydrocarbon. A 1 is implied even if it's not there. So I'm going to draw in that 1 here, and then I'm going to double that to 2. I'm going to double 4.5 to 9, double 3 to 6, and double this 3 to 6. So now my balanced equation is 2C3H6 plus 9O2 gives me 6 CO2s and 6 H2Os. And that is the correctly balanced equation.